Swayam Prabha. Digital India. Educated India.
Welcome. So, in this lecture of module 9, we'll study a simple problem. So, we'll do a simple problem by hand, and then we'll see how if I increase the number of degrees of freedom, then how the solution changes. So, first we'll go for a plate with a uniform axial force. So, to describe the problem, so let us consider a simple plate. So, thin plate, or rather I will say it's a 2D problem. So, let us consider a thin plate. This plate is fixed here. So, it is fixed here. Now, this plate is also loaded with an axial force, that is say P0 force. So, P0 is 10 pound per inches, and then you have the length of this plate is 120, and height, or whatever you call the width of your plate, is 160. So, now this plate, you need several information for this plate. So, first of all, the thickness of the plate, let us say thickness of the plate is 0.036 inch. Okay. So, that is the thickness. Now, the Young's modulus E is 30 into 10 to the power 6 pound per inch square. Now, you need Poisson's ratio also. So, 0.25 is the Poisson's ratio. So, now this plate we want to solve by finite element method. Now, to solve it by finite element method, obviously we need to assume that since this is a plate, thin plate, so it is natural to assume it's a plane stress problem. So, the plane stress, so this problem definition tells us that it's a plane stress problem. So, plane stress problem. Now, the plane stress problem, we know constitutive matrix, which is C is 1 minus mu square, then 1 nu 1, then 0 0 0 0 1 minus nu by 2. So, that is my constitutive matrix. Now, if I put these values, the constitutive matrix, I can just compute the constitutive matrix. For instance, the constitutive matrix will look like this, that is 10 to the power 6. If I take outside, then this looks 32, 8, 0, then 8, 32, 0, then 0, 0, 12. So, this is my constitutive matrix. So its unit again is unit of Young's modulus, that is pound per inch square. So now the next step is that, so the constitutive matrix is known to us. Now the next step is that I want to now discretize this body. So there are several ways to discretize it, but since we will be doing it by hand, so it is better to do it with a lesser number of elements. So let us discretize. The first step is to discretize this problem. So let us consider two elements such that this is my discretization. Now this is 1, 2, 3, 4 is my number of nodes, and this is element number 1, this is element number 2. Now obviously I have discretized with triangular element, so linear triangles, say not linear triangle, the constant strain triangle, that is 3-noded triangle element. So for which I know the shape functions, that is psi I is my 1 by 2a, that is element this thing element area, and then alpha I plus beta I x plus gamma I y. So we know this. Now what we need to find out? We need to find out there is no body force in this body. So it is assumed that there is no body force. So body force term, that is your, if you remember that if E term will be essentially 0. So what are the extra term we need? What are the other terms we need? We need the stiffness matrix and the traction vector, that is your elemental traction vector, the force vector which will act as a force vector. Now among these, so we know the coordinates of these points. So let us say this point coordinate is 0, 0, then this is actually 120, 0, and this is say 120, 160, and this coordinate is your 0, 160. So you have these coordinates, you know. So now if you remember this alpha I, beta I and gamma I, for this is for I equals to 1, 2 and 3, so 3 shape functions. So these alpha, beta and gammas we can calculate from the coordinates. Now how many degrees of freedom this will have? This will have two, this each node will have 2 degrees of freedom, that is my u1 v1, then you have u2 v2, so u2 v2, then you have this one, that is u3 v3, and you have v4 u4. So you have total 8 degrees of freedom. Now among these 8 degrees of freedom, this side of the plate is fixed. So this degree, the displacement at these two nodes will be naturally 0. So what is the condition for that? That means that u1, v1, u4 and v4 all are 0. So effectively we have 4 degrees of freedom to solve it. So now, so naturally my reduced stiffness matrix will be 4 by 4. So now let us consider now from the each element. So our first job is to find out the elemental stiffness vector and elemental force vector. So before doing that, so what are the, from the data we call the pre-processing of the mesh. So that pre-processing of the mesh required several things, that is the coordinate matrix of this discretization. So the coordinate matrix or the coordinate vector will be, so this is say our node number, so x coordinate, y coordinate. So why I am doing in this way? Because this is the way we program it in the software or the programming language. So you need to input these things because you need large, so in the computer solution, or means you need, if you increase the number of elements, then you need to input in this way. So node number 1 you have 0 0 is the coordinate. Then node number 2 will have your 120 0. Node number 3 is 120 160. Node number 4 is 0 160. So the procedure is very similar if you increase the number of elements. So now another thing you need is the connectivity matrix. So the connectivity matrix also you need. So what is connectivity matrix? The connectivity matrix means you need to find out the how each elements are connected to each other through the degrees of freedom or the node number. So we know that each node is having 2 degrees of freedom. So suppose I have for this discretization, so what will be the thing? So we'll have the, instead of node number you will have the element number. So element number, then you will have the local connectivity, how it is attached. So let us say it is at a 3 node. So 1 2 3. So this is the connectivity matrix. So let's say element number 1. Element number 1, the local node. So let me give it a different color. So this is local number node 1, node 2, node 3. Now this is local number node 1, node 2 and node 3. So now my connectivity matrix will be your, for element number 1, so this is 1 2 3, it coincides. So for element number 2 it is 1 2 and 1 3 1 3 and 4. See, these things are global degrees of freedom. So these are global degrees of freedom. Global node number essentially. So global node number, and these things are essentially the local node number. So that means the heading itself is local node number. So suppose you have discretized with 4 noded elements. So naturally the local node number will be 4, 1 2 3 4. So similarly, if you have 6 noded triangle, 8 noded quadrilateral or any other element, the number of columns in this matrix will increase according to the element type. Now you have these two things, you have to enter these two things, you have the E and nu, so you know what is the constitutive matrix associated with it. So now the first step is to compute the elemental stiffness matrix. So the first step is to go through the element wise. So how I will do that? So first let us consider element number 1. So in the element number 1, what is the formula for or the expression for stiffness matrix? Because we have seen this stiffness matrix in the previous class. So that is your elemental stiffness matrix is essentially T. T is the thickness, or H is the thickness, then integral of B transpose C B. So that is my dx dy. So it is over the area. So now B from constant strain triangle, what is B? So B is my, as I have the B matrix is my differential operator, that is del del x 0 0 del del y and del del x del 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 y del del x. So this multiplied by your shape function matrix. So shape function matrix is psi. So naturally my psi will be of this form: 0 psi 1 0 psi 2 0 psi 3 0 and then 0 psi 1, 0 psi 2, then 0 psi 3. How it is come, how it has come, that also we have discussed. So now the B matrix, if you do that, then what will happen? So psi 1 is alpha 1 beta 1x plus gamma 1y. So if I take the derivative with respect to the x of psi 1, then only beta 1 is left. So naturally this one will be something like this, that is beta 1, then again 0, 0 and then 0 and then you have gamma 1 because it's a linear function, so constant, then again you have gamma 1, then you have beta 1. So like this you will have for all these submatrices, that is your beta 2 0 0 gamma 2, then gamma 2, then beta 2. Then you have 0 beta 3 0, then you have 0 gamma 3, then gamma 3, then beta 3. So this is your B matrix. Now what is my beta 1, beta 2, beta 3 and gamma 1, gamma 2, gamma 3? So beta 1 is my y2 minus y3. So what is my beta 2? Beta 2 is y1 minus y3 minus y1. Then what is my beta 3? Beta 3 is my y1 minus y2. Similarly, gamma 1 is minus beta x2 minus x3. Then gamma 2 is my minus y x3 minus x1. Then gamma 3 is minus x1 minus x2. So now you see for triangle, first triangle, that is my this triangle, you know everything. For this triangle, this coordinate is 0 0. So this is my node 1 2 3. This is my 120 0. This is my 120 0 and this is my 120 160. So if I substitute this thing, my beta matrix, I can compute for the beta matrix. So if I do that, then again the area is also you have to calculate. So calculating area of a triangle with 3 coordinates known, you know what is the formula for calculating area of the triangle, and this is for simply for this area is 9600, because you can check by calculating half of height and the base. So now if I compute the B matrix, that is strain displacement matrix, then what will happen? I can by just substituting this coordinate x1, x2 and x3, I can compute the B matrix. So B matrix will looks like 1 by 2 into 9600 divided by not divided by, so that is the matrix. So that is my minus 160 0, then 160 0, then 0 0, and then you have 0 0 0, then you have minus 120, then 0, then 120, then you have 0 minus 160, then you have minus 120, then 160, then 120, then 0. So this is my B matrix. So once I have this B matrix, then the next thing, so if you see that I have now my B matrix ready, and then I have also my C matrix, which is also element wise constant here, because I have taken the uniform property. So this property, that is homogeneous problem. So That means I have no variation of Young's modulus and Poisson's ratio over an element. So now this equation can be simplified. So this is a constant matrix, this is a constant matrix, and this is also a constant matrix. So finally I can write this is H A is B transpose C B. So once I know this, then I can get my final stiffness matrix, that is K1 for element number 1. So how to calculate? That is the multiplication of this B, C and B transpose C and B. So if I do that, then I will get the matrix, so which will look like something like this, that is 10 to the power 4. So you can just do this calculation and I will just give the entries. So 76.8, then 0, then minus 76.8, then 14.4, then you have 0, 14.4, then you have 0, 28.8. So you can check if that is correct or not. So minus 28.8, and then you have minus 21.6, then this is 0. So stiffness matrix will be 6 by 6 stiffness matrix, because you essentially have 6 degrees of freedom per element. So that is minus 36, and then minus 16.2, and then you have minus 14.4. So then again you have 14.4 minus 28.8, then you have minus 36. So it is a symmetric matrix. So 72, then you have 21.6, and then 43.2. So 43 point, this matrix I am just writing because you can verify it. So 0 minus 21.6 minus 16.2, then you have 21.6, then you have 16.2, then you have 0, then you have 14.4, then you have 0 minus 14.4, then 43.2, then you have 0, then 43.2. So this is my matrix. So this is a 6 cross 6 matrix. Now this 6 cross 6 matrix I have got for element number 1. Now this is corresponding to degrees of freedom, which are the global degrees of freedom. So if I now write that this is the corresponding 1, corresponding 2, 3, 4, so and 5, 6. So this is according to connectivity. How I get? Because node number 1 is actually element, local node number 1 is elements global node number 1. So that means the global node number 1 is actually the elements local node number 1. Global node number 2 is actually elements local node number 2, and similarly for node number 3. So that's why I can write this thing. Now once I have this thing, the next thing is I have to calculate now the traction. So traction, what is the formula or what is the expression for traction? Because if you see, this is the force is given, so 10 pound per inch along the this line. So it is multiplied by thickness essentially, because thickness is separately given. So 0.036. So it is already multiplied by thickness, so we don't need to multiply thickness. So the that QE or the QE vector is here QE1. I can write that is integral over the lambda or the gamma. Then I have my psi transpose, then you have Tx and Ty. So this is over ds. So this is my traction. So psi transpose, we know what is the psi now, and now I have gamma, and then psi transpose only I have Ty is 0 because only axial load is there. So which I can just write it like 10, then it is 0, then this is ds. So now psi is what we know. So if you look for this element, so node 2 and node 3 is having the force, that is this force is having this. So naturally my multiplication with 10 and 0, so this is now is your 6 cross 2 matrix. So now if I multiply with it, my psi 1 will be 0, psi 2 will be, so this finally means that integral of 0 to L23, because length of this 23. So L23 is my 160, and then psi transpose, then you have 10, 0, then you have ds. So essentially I am taking this and this. So my axis is something like this. So this is my axis, local axis on this side of the beam that we have, this side of the element. So this I have explained you in the previous class. So if I do that, then naturally my phi 2 and phi 3 will play into role, means phi 2 will be my phi 1 will be 0, and phi 2 will be my 1 minus s by 160 is my length, and then phi 3 will be s by 160. So this is my phi 1, phi 2, phi 3. Now if I multiply with this and this, then this will look like something, the final outcome of this will come like this, that is if you integrate with phi 1, phi 2 and phi 3, then it will look like this, that is your 800 0 0 800 0 800 0. So this is my 6 cross 1 vector. So here that is s 1 minus s, that has to be integrated somewhere. So 1 minus so s minus s square by 2 into 160, that if I substitute 0 to 160, it will come like this. So now once I know the traction vector matrix, then I have the elemental equilibrium is something like this, that is Ke equals to your UE, that is your nodal force vector, nodal degrees of freedom, and then you have QE. So I know everything here, this quantity I know, this quantity I know. So elemental equilibrium for the first element is done. Now I go to the element 2. So element 2, if I follow the same procedure, I will get the stiffness matrix. So first the area is same, that is 9600, and then you have your B matrix. So B matrix will something look like this, 1 by 2a. Now this is 0 0 160, then you have 0 minus 160, then you have 0, and then you have 0 minus 120, then you have 0 0, then you have 000 120, then you have minus 120, then you have 0 0 160, then you have 120, then minus 160. So this is my B matrix. So once I know B matrix for this, the similar procedure, if you compute the stiffness matrix, then I will get my K2. So K2 will look like something like this, that is 10 to the power 4. So again a 6 cross 6 matrix will come. So 16.2, 0, then 0, then you have minus 21.6, then minus 61.2, then you have 21.6, then you have 0 43.2, then minus 14.2, then 0 14.2, then you have minus 43.2, then 0, minus 14.2, then 76.8, then again 0, then minus 76.8, then 14.4, minus 21.6, 0, then 28.8, then you have your 21.6, then you have minus 28.8, and then you have minus 16.2, then you have your 14.4, minus 76.8, then 21.6, then you have 93, then you have minus 36, then you have 21.6, then minus 43.2, 14.2, then minus 28.8, and then minus 36 and 72. So now this is my second stiffness matrix. So if I do this, then what will happen? The entries are correspond to which degrees of freedom. So now if I draw the element, then this looks my element. So this looks my element. So this is my thing. So this is my 0, this is my 120, 160, then this is my 0, 160. So now this is my local coordinate, which is correspond to global coordinate, that is 1, 3, and then 4. So naturally these degrees of freedom will be your 1, 2, 5, 6, 7, 8. So now according to these global degrees of freedom and local, so similarly I can write it 1, 2, 3, 4, 5. So this UE here, this UE for this element, the U vector, that is UE vector, will be something like this, that is U1, V1, U2, V2, V2, U3, V3. Now here the degrees of freedom will be your UE vector will be something like this, that is U1, V1, U5, V5, U2, V2, U3, V3, then U4, V4. So this is my this thing. So this is essentially corresponding, this 1 corresponding to U1, 2 corresponding to V1, then 5 corresponds to U3, 6 corresponds to V3, then this is U4 and V4. So now if I have to assemble it, that is my final global stiffness matrix, that is Kg. And now note here that here the QE that is your Q2 will be 0 vector, that is because there is no external force acting on this element. So there is no external force on this element. So this element, these two sides, and this is an internal side, so which will cancel finally. So finally I have to assemble this K1 and K2. So assembling I have to do, so that is according to the connectivity, the element number 1 to 2, I have to assemble it, the local element stiffness matrix. So as per connectivity, if I assemble it, and then if I put the boundary condition, so final global stiffness matrix will be my 8 cross 8, because all of them are 6 cross 6, element stiffness matrices are 6 cross 6, then finally the global stiffness matrix will be 8 cross 8. Then I have to put the boundary condition, so I have to take the reduced stiffness matrix, the procedure of which has been already described. So now once I do that, then I will be living with the 4 variables which are having known boundary values, so which are U1, V1, U4, V4. So then finally I will have my 4 cross 4 K reduced stiffness matrix, that is my 93, then minus 36, then minus 16.2, then 14.4, then you have minus 36, then 72, then you have 21.6, and then you have minus 43.2, and then you have minus 16.2. This is also a symmetric matrix. So remember that symmetricity is an important property, because this will stop the this will reduce the factorization cost. So because you have already you have already studied the different factorizations, like your LU decomposition or LDL decomposition, whatever it is. So U2, so my unknown degrees of freedom, U2 V2 and U3 V3, then you have something like this, that is the global right hand side, that is 800 0. So now if I solve this equation, then I get U2 V2, U3 V3. So after solution, so solution can be done by, this is a simple problem, so you can take an inverse, and then so there is a 10 to the power 4 here. So you can take the inverse of it and then pre multiply with this vector, but that is not usually done in solution of systems, because inverse costs more. Not only that, inverse is sensitive to the these entries in the matrix. So now if I do that, then what I will get is something like this, that is U2 V2 U3 V3. So if you look carefully, then this solution is little bit, so it is 11.28, then 1.97, and then 10.10, and then minus 1.09. So now let me draw the problem again. So essentially we are constructing this is my problem. So I am just giving an uniform force or uniform traction along this side P0. So naturally this is my U2 V2 and U2 V2, and this is my, sorry, this is my U3 V3, U3 V3, and this is my U2 V2. So and this is my fixed body. So now if you have a uniform traction, then the solution at this point and this point should be equal actually. That means the U displacement will be actually equal, and the V displacement will be sign changing, because due to this extension of this body, the top point, that is node 3 and node 2, node 3 will come down, and node 2 will come up. So naturally sign change will happen, but the magnitude will be remain same. But if you look the solution from here, that is U displacement are different. So this is due to the mesh is not symmetric. Mesh plays an important role in the finite element solution. So this is the mesh, this is the mesh. So this mesh is not a symmetric mesh. So this is why we have the problem here. Now this is the overall procedure of finding out displacement. Now again, once we find out the displacement, you can find out the stresses, because stresses has to be element wise calculation of stresses. So how we can calculate the stress? That is sigma vector. So that is equals to your B, you know, so C, the C matrix into epsilon vector. So C matrix you know, and then you have the epsilon matrix, which is which I can write as B matrix into the UV vector. So this for element number, different element number 1 and element number 2, I can compute the stress and strain vector I can compute. So naturally these stresses and strain vectors will not be varying, will not have any variation over an element, because it's a constant strain triangle. So naturally this will be constant. So we have a jumps on the stresses and strains. So in case of a quadrilateral element, you will generally evaluate stresses at the Gauss points and then extrapolate it to the node. So now now what I wanted to show you is that if I refine the mesh, then how the solution changes. For instance, here I have a discretized with two 4 element, then you see this is the contour plot of the u displacement, then this is the contour plot of v displacement. Even though this mesh is symmetric mesh, so this is the displacement how it changes. Now if I just refine again the mesh, then you will get this. So you will see that how the displacement is becoming smooth slowly, so because of the number of degrees of freedom present in the solution. So now you see displacement is also changing. Now if I continue this process and then if I plot how u and v displacement changes with the mesh size, then you will see a converging pattern, that is from after some time or after some deduction on the element length. So this is basically the element length, is this is my element length. So if I reduce the element length and plot the displacement, then you will see that solution converges to at a point. So then we can say this is a converged mesh. So now this is a very fine mesh I have done. So this very fine mesh, if I use the displacement, you will see that this displacement looks like this. Now this is the stresses, this is sigma xx, which is expected because this will produce a constant stress because it's an axial problem. So here you will have the boundary effects. Because of the boundary, there is a stress variation which is known as Savena effect also in elasticity. So here also you will see that sigma yy has some variation. Similarly, you will have the sigma xy. Now if you look at the displacements have nearly converged to the solution. So if you further increase the mesh decrease the mesh size or increase the number of degrees of freedom or the number of node and number of element, you may not get a very may not get a better solution. So that's how we say that a solution is converged to a particular mesh or not. And naturally, this is not the best way to check the convergence of the problem, because we are checking at a particular point on the body. So in principle, it has to be checking. It has to be checked at the overall domain. So over domain. So for that, what we do, we calculate the norm or the displacement norm or the energy norm. So that's how we try to find out how the solution changes. So this part will be discussed later, actually, how in the error analysis on finite element method. So this is what I wanted to show you, that finite element method is actually not for calculating by hand. You have to do it in the computer, then only you can get the full picture of the solution. So now I have discretized this problem with a triangular element. Similarly, if I discretize this problem with a quadrilateral element, for instance, I can discretize this problem something like this. So with a single element I can discretize with 4 element. So 1, 2, 3 and 4. Then we can also find out the solution for this problem. And for the triangular element, for the rectangular element, we know the shape functions, which are phi i's are 1 by 4 ab, and that is your 1 minus x by a into 1 minus y by b. So minus plus minus plus. So basically this is the shape function for an element which has something like this. So that is your this length is 2a and this length is 2b. So if this is the case, then you have this. This is the axis. So these coordinates are minus a minus b, then this is a minus b, then this is ab, and this is minus a b. So this is node number 1, node number 2, node number 3 and node number 4. So for this case also we can exactly integrate and find out. You can check this how solution changes. Now in the most of the cases we cannot compute the exact integral, and for that you have already studied how to find out this integral with the Gauss quadrature. For instance, if I have a discretization which is actually not quadratic, that is my something like this, if I start discretizing it something like this, then you will not able to means you can find out, but that's a tedious job, so nobody tries to do that. So something like this, if I try to now solve this problem with for this discretization, I have to use Gauss quadrature rules, and naturally the Jacobian and all those things you have to calculate. So that is already we have studied. So my objective is for this lecture was that just to show a problem which by hand you can do it, but naturally this kind of problem which is very large number of elements, we cannot do it by hand. So for that we need computers to solve those problems. So that's all. I stop here. So we'll meet in the next lecture. Thank you.